Hello students, so today we will be discussing about the magnetic properties of nanomaterials or magnetic nanomaterials in short. Now, magnetic nanomaterials have got many applications like high density magnetic storage, random access memory, can be found as ferrofluids, spintronic application, magnetic semiconductor robots and magnetic resonance imaging. Now, any magnetic material, it depends on the properties that depends upon the shape and size of particles. Now, if we take an image plot or hysteresis plot, the strength of the magnetic field can be defined by three terms: the coercivity, the saturation magnetization, and the remnant magnetization. Coercivity is the width of the hysteresis loop, and retentivity is the value of the magnetization when the field is made zero, and saturation magnetization is the maximum magnetization that has occurred and which can be visible through the plot. Now, all these regions have been marked. Now, another quantity that is important to understand while discussing magnetic properties of nanomaterials. One is the susceptibility. Susceptibility is the ratio of magnetization magnetic field applied. So this is mainly used in Tesla, and this is mainly in AMU program. And so it determines what is the property of the material. Like if the material is less than zero, it is diamagnetic. More than zero, it is paramagnetic. But less than one. Similarly, magnetic retention indicates how much as the magnetic field been able to magnetize the material, and MS is saturation magnetization, that how well the alignment takes place, how well the alignment of the dipoles take place. Now, when there is a decrease in size of the there is a decrease in grain size, it has been found that the coercivity value has been found to decrease as well. However, the saturation magnetization doesn't really change. Now, the reason of in case of soft magnetic alloys, nanocrystalline alloys, which are used for device and switching, they have a very small hysteresis loop, and this is mainly due to the fact that if there are cooled grained, then the volume fraction of the grain quantity is much lower, and magnetic field is the one which is involved in causing causing spinning of the grain quantity regions. Now, in the case of nanomaterial, what happens is that the domain size is much much more than the grain size. Whereas in case of coarse grain materials, the domain size is equivalent to the grain size. So all these factors lead us to the property that the magnetic anisotropy gets averaged out in nanomaterials, whereas in case of soft magnetic alloys, what was the reason that the material didn't show any or less coercivity was the fact that the magnetic field was not able to pin the grain boundary regions because of their increased volume fraction. However, in the case of nanomaterials, although the volume fraction of the grain boundary is increased due to the much lower size of the grains compared to the domain size, the magnetic anisotropy is averaging out, and it leads to a decrease in Hc as well. So Hc decreases in case of soft magnetic alloys, and Hc also shows a decrease in the case of nanomaterials. We will discuss one of the amorphous, very common amorphous alloy comprising of five transition metals apart from boron and niobium, which are four transition metals, also in silicon. So here, in fact, Fes and to some extent copper transition materials. Now this amorphous alloy, when annealed, it transforms into an FeC compound, which is having a BCC phase. So crystallization to take place, but the fact that the grain growth is not that much as it should have been. The reason behind this is the presence of these two elements, where this copper is indication of nucleation, whereas this niobium it retards the grain growth. So that is why we get the non-crystalline FeSi BCC alloy. There are materials called fine met, which have a very low pore loss and are high saturation magnetization. Therefore, useful for high frequency applications. In non-crystalline fine met, however, the saturation magnetization value goes down. This is due to the attendant of amorphization. In case of fine met, they move towards this amorphous region more, so that's why there is a decrease in the resolution magnetization. Okay, so this is actually a problem that if we are making nanomet, fine met, which is having all of the properties, but this reduction is causes a problem. So a solution has been framed or was found out to find out to discover a material called nanopalm. Now the word nanopalm is made up of two words. It's nano and palm. So it basically represents those material which when synthesized in nano crystalline form, they remain in that form. And to do that, what was most important was to increase the percentage of iron in it. So increasing the percentage of iron to 80 to 90%, the saturation induction value showed a large increase. There are other types of alloy, like also nanopermanent nanocrystalline alloy has got applications. It shows low energy loss at high power frequencies of 60 Hz. Another type of magnetic material is a nanocrystalline iron, which is basically a single domain iron. Now, the advantage of these structures is that they are used in low energy losses devices, low energy losses, they themselves cause very low energy loss. And synthesis of these can be done by rapid solid depletion techniques, where amorphous ribbons are found. Now you can see this is how the amorphous ribbons in the nanocrystalline phase, and we see the increase in temperature, although it increases the saturation temperature, the saturation value. It is higher magnetization has taken place, this gap, but there has been a reduction in the width because of surface flux results. Usually, another aspect of magnetic material is the remnant magnetization, that is the MR. That is how much of magnetic field effect is still present in the material when the magnetic field has been removed completely. Now, MR is usually much more than half of the saturation magnetization. In fact, in some cases, it has been found that MR is close to MS. Now, uh, a nanocomposite where both hard and soft magnets are taken and formed. So these type of composites they experience on the involved in something called exchange coupling. Exchange coupling is the coupling of electron at the interface. Since a lot of different phases of are formed while we are joining these compounds in different spins. One that interfaces are very much important because they belong to none of the two phases, and from here this exchange coupling takes place. Then we have Fe-rich amorphous alloys like Fe90, 7 and 3, which has two different parts. One is hard and another is soft. Soft is simply the iron phase. So it is called a two-phase nanoscaled ferromagnetic line. Another type of nanomaterial is using rare earth, yttrium, samarium, and cobalt. They produce magnets with a large surface area. Also, samarium cobalt magnets are also useful. They involve the production of high power on being used on the rare earth metal being used. They're also used in submarine automation, power gas, MRI gas sensor. Superparamagnetism is another aspect of magnetic material. So the material having superparamagnetic effect is actually a weak magnetic field. So neither is the Hc small, neither is the magnetization, substitution magnetization small. So if the ferromagnetic material is the grain size of the ferromagnetic material is reduced, it has been observed that formation of this superparamagnetic material takes place. And for comparison, these two schematics have been drawn together. So the red one is of the paramagnetic material, the ferromagnetic material, and the blue one at its middle is of paramagnetic material. Now, when the grain size is reduced to a much lower extent, then there is formation of spin flip. As previously told, the magnetic anisotropy is cancelling out. So in this case, the spins they start cancelling out, and that is why the coercivity goes down. However, the retentivity is still rising. Magnetic field superconductors, if they are put inside magnetic field, they show total exclusion of magnetic field provided the temperature is less than the critical temperature. And the magnetic field is also less than the critical magnetic field. Now, due to Marsden effect, the magnetic lines of force may not may bypass each other because they are not allowed. This is actually can be considered to be effect of showing superconductor superparamagnetic behavior. This is what happens in the case of a superparamagnetic. The only thing is that the saturation or the MS value is much lower in the case of paramagnetic materials. Okay, so this can be called as superparamagnetic material with a susceptibility value -1. Another type of aspect of magnetic nanomaterials is in the form of thin films. Alternate distribution of ferro and antiferromagnet films may lead to a shift of the hysteresis 2, which is called exchange bias. The shift mainly occurs due to the pinning of magnetic dipoles at the interface. In 2D conductors, there is a phenomenon that is called quantum Hall effect, where the conductance of the conductor is represented as E squared by 2h, and we do have some electronic energy levels being developed due to this, and these are called Landau levels, which have got a certain value and called Landau conductivity. And this is basically coming from Hall effect. Hall effect is a phenomena where a conductor carrying current in a certain direction, if exposed to a magnetic field perpendicular to it, then it will produce a voltage which is perpendicular to both magnetic field and addition of current, as this is what has happened here shown. And numerically the value can be expressed as the multiplication of current and magnetic field divided by the charge of the carrier and time.